Recording in progress.
Sorry. Okay, so first I want to talk about uniform circular motion. Okay, so uniform circular motion, in contrast to all of these projectile problems where things are falling or throwing or something like that, uniform circular motion, as the name implies, refers to cases where your motion looks like, let me draw a better circle. Good. Looks like this. And so I have something like, I don't know, I think a good concrete example is something like a satellite or something, where I have an object, this is my little satellite, that's going to move in a circular path for a continuous duration. And that circulation is going to always be around some center of rotation. So we're going to go ahead and label that point the center of rotation. Okay. So there's a couple of things that are kind of weird about uniform circular motion. So the first one, I think we know what to expect, which is that if I wanted to just give the position of the satellite as a function of time, I would just draw a straight line vector from my center of rotation to where my particle currently is, right? So right now it's sort of aligned with the x-axis, so it goes there. But you can imagine sometime later, maybe this satellite goes over here, so it's here. So in that case, my vector would now point. So if I move here, then my radial vector now points there, right? So just like always, the location vector, the position vector always just points to wherever the object currently is. And at this time, it looks like it's pointing just straight towards the satellite. Okay, so this is interesting because that suggests that in uniform circular motion, points to orbiting object. But we know that, this is a circle. So this distance in principle is the same as this distance, this distance, this distance, right? It's the definition of a circle. So interestingly enough, the magnitude of r, which sometimes you'll see me denote as just lowercase r with no vector symbol, that's actually constant. But r itself, which is a vector, is not constant. And this is, I think, the crux of what makes these circular motion problems kind of annoying, is that it's all about the fact that the things that are changing are really directions, not magnitudes of things. And in principle, it might seem straightforward. I was going in a circle, of course, its position is changing, but keeping track of what's actually changing is, I think, where these problems get a little bit tricky. Okay, so that's the position. It goes in a circle, makes sense because the object is orbiting. Okay, so now we want to do the speed. I'm going to go ahead and close this door just because it's outside. So. And hopefully the classroom starts to cool down some. It's really hot in here. Okay. So if I have an object that's orbiting over time, one thing we might ask is what that object's velocity looks like. And this is where we're going to start with some intuition, but then we're going to try to back out exactly why mathematically this happens. So if I think about my little satellite thing, it starts out here. Sometime later, it ends up here, then here, then here, then here. So its position is moving along the circle. But if I think about how it changes and went from here to here, or here to here, or these tiny little increments, it's actually always moving in a direction that is tangent to the circle. And this is, again, something that I think is a little confusing about circular motion, which is that your radial vector, or your position vector, sort of follows your object, but then your velocity is always going to point orthogonal to that vector. So I'm actually going to draw a right angle here. So what does that mean? That means that here I show, my object is just here, right? And so I say that my velocity vector points up. But then if I were to redraw this whole thing, so let me just draw another point in the orbit like here. And let's call that, something like maybe r of t plus delta t. At this later time, you can see obviously my position vector changed because I moved locations. But at this point, I would draw that my velocity now points orthogonal to the new position vector. Okay, so the velocity is always going to point off the circle. And I call this tangent to the circle. This isn't tangent in the sense that we saw on trig. Here, referring to tangent in the sense that it just barely sort of grazes. So here, I call this tangent because this line drawn parallel to this vector touches the circle just there. It's just a convention that you might recognize from trig. So basically, no matter where I am on this circle, it's always going to be the case that my velocity vector at that point in the orbit always points just orthogonal. So I'm just going to draw a couple of examples so you can see what I mean. Okay, and so throughout all of my rotation, right, I have this condition where my velocity is always pointing sort of along the circle, what I call tangent to the circle, and my radial position vector is always just pointing towards my object. And those two vectors are always at right angles. So I'm going to just go ahead and write that down, which is that V is perpendicular to R. This symbol here, you might recognize it from trig or something. This just means that these vectors are perpendicular. Okay, so that's a little bit weird, but one thing that's nice about the uniform and uniform circular motion is that we can do a very similar thing that we saw again for the radial position. So just like we saw here that, I'm always the same distance from the origin, all that changes is my directionality. The same is actually going to be true for the velocity. So the magnitude of V, which I'm just going to call V with no little hat on it, that's constant for uniform circular motion. But again, V, the whole vector, is not constant. Okay. So uniform circular motion basically satisfies this, and this are your sort of defining features of uniform circular motion. And these three statements are equivalent to this diagram I'm drawing, where I'm always sort of moving at a constant angular speed. My position is changing, right, because I'm moving in a circle, but my velocity is always tangent to the circle, and it's always at a right angle to my position vector. Okay, so given that we have given that we have position versus time, which is changing, we have velocity versus time, which is also changing. Speed stays the same because that's the normal velocity, but the direction of the velocity itself is changing over time. The fact that velocity is changing implies that we do have acceleration in this problem. So changing V implies we have acceleration. Okay, so now we want to figure out what the acceleration of this problem is doing. And intuitively, it kind of makes sense, right? Velocity is changing, so something's causing the velocity to change. So let me go ahead and actually, I might just redraw my diagram. Okay. Great. So it's my center of rotation. And let me just try to draw this as nicely as I can, because these circle problems are harder to draw. So let's say that this is what I'm going to call R of t. So this is my little satellite thing. It's not a very good satellite. And then let's say sometime later, I'm going to try to draw this small-ish. So let's say that this is R of t plus delta t. So delta t is just some small amount of time has passed. So I've moved a little bit along that circle. So now my satellite is here. So then if I draw my vectors for velocity, and I'll use different colors just to make this easier to see. So let's call that V of t. And again, that's at a right angle there. Then sometime later, I should have V of t plus delta t. And again, these are both at right angles there. Okay, so I've defined my coordinate system such that my position changed, my velocity changed, but both we know are changing only in terms of their direction, not their magnitude, because everything's uniform and uniform circular motion. Okay, so we can write that out using what we know is the definition of acceleration. So recall that acceleration is a vector, which is defined as the limit as delta t goes to 0 of velocity at t plus delta t minus the velocity of t divided by delta t. And this is the same definition we saw in kinematics. So we're starting from the same principles. They just look a little bit different here. And the idea here is that here I drew this nice, diagram where the object moved, that whole angle that looks like 30 or 20 degrees or so. But in principle, we're really interested in the limit where that is a tiny, tiny infinitesimal change along the circle. Okay, so really we're going to call this angle here delta theta. And we're going to be taking the limit where delta theta is vanishingly small. That's what this that's what this limit here corresponds to, is the case where that amount of change is getting infinitesimally tiny. Okay, and so as a result, one thing that we would say is that as delta t goes to 0, delta theta also goes to 0. That's the limit that we're taking there. Okay, so this next part, every book has a different way of doing this. I'm going to use a similar triangles method. The Knight textbook does this a little bit differently, but I think that this is something that it's just to show where this comes from. But once you've seen this, just remember that this is the case for uniform circular motion. Okay, so I'm going to draw a couple of triangles to try to represent this. So I'm first going to take this case where I have my triangle here and here, and I'm just going to blow it up so we can see it a little bit better. Okay, so this is super hard to draw, but let's say I have r of t. This is r of t plus delta t. And then this difference here, oh no. This is going to be delta r. So that's going to be the vector that takes me from this plus this gives me that vector. So I'm just calling that delta r, because equivalently I could define this as this vector minus that vector, right? I'm just doing vector arithmetic there. And then I still have that little delta theta in there if I want. Okay. So that's the draw. So that's just me taking this diagram and blowing it up. So now I'm going to take a different diagram and blow it up. So now I've drawn this, and this here. So now let's do the exact same thing with the velocity vectors. And this is where things get weird, because my velocity vectors look like that and that because they're always orthogonal. So I'm going to change colors for this and try to draw this as much to scale as I can. So it looks like my initial velocity vector looked like that, because I'm just taking it from here. And then my other velocity vector looks something like that, which means that my delta v, which is defined as just this minus this, that should just point head to tail there. So I go from v of t plus delta v, and I got my other vector back. So just doing vector arithmetic here. And so again, this first diagram is just me drawing this out, but the second diagram is me trying to take this and this and draw them next to each other so we can see how that velocity is changing. So it's a little bit of a, I don't know, abstract diagram. Okay, so this is where some magic happens, because it actually turns out that if you go through these triangles and sort of solve them out, this angle here is the same as this angle. And so it turns out that this triangle and this triangle are similar triangles. And so, similar triangles have their own lore, but I think that the most important thing to know for our purposes, right, is what do we know about triangles? So we know that the length of this is the same as the length of that, right? The velocity's magnitude is always the same in uniform circular motion. It's just the direction. So the length of that triangle is the same as that. And then we also know that the length of this is length of that, because if I go in a circle, my radius is always the same. So you can use, your favorite isosceles triangle tricks to back out that it needs to be the case for two similar triangles, that delta v over v equals delta r over r. And it's because of similar isosceles triangles. And this is something that you can take a little bit of time and improve this if you're not convinced. But basically, since these are similar, you could always drop a height and then actually solve for the similarity in the triangles if you're so inclined to do it. But this ends up being the big relationship we need to proceed on this problem of finding the acceleration. Okay. Yeah, what's up? Only in uniform circular motion. So only if it's going in a circle at a constant speed. Yeah. Okay. So now that we have this relationship, we can make a little bit of progress on our equation here. So again, we're just trying to find the acceleration. So we're going to start by doing this purely in terms of magnitudes because this is the most important equation. Then we'll get back to this. So I'm just going to focus for now on A, which is just defined as the length of that vector. So how big is the acceleration as a vector? Okay, so this is going to be equal to the limit as delta t goes to 0 of v of t plus delta t minus v of t over delta t. So I've just taken the length of that vector because I want to do direction separately. Okay, so you'll recall that up here, I defined delta v as just equal to the difference of those two vectors. So I'm going to go ahead and simplify this and just write that. I'll zoom out so that's easier to see both. That's equal to the limit as delta t goes to 0 of delta v over delta t. Okay, so now I can make some simplifications using this relationship here, right? Because I now have an expression for delta v that I can substitute in, and this is going to come in super handy. Okay. So A is equal to the limit delta t goes to 0 of delta v over delta t. And then we know from up here, actually, let me get rid of this, that this is the case. And so now I'm going to go ahead and plug in and say that this is the limit as delta t goes to 0 of v over r delta r. So this is just me moving this over here, and then that gives me a formula for delta v. Okay, so this is nice because now I have something that I can simplify, right? So I know that v and r are the magnitude of the velocity, and the magnitude of the r is uniform circular motion. So I know that those are both constants. Oh, and I missed a delta t over here. So I can write that A is equal to V over R of the limit as delta t goes to 0 of delta R over delta t. And so now I can use the fact that this is the definition of speed to simplify this and get that A is just equal to V over R times V. And so I get, let me do this on a new line. A equals V squared over R. For uniform, I'm going to emphasize uniform because there are cases that we'll see in the future where things don't move at a uniform speed. For uniform circular motion. So this is a super handy formula, right? So this is basically saying that if I know how fast I'm orbiting, right, how many kilometers per second I'm constantly orbiting at in that uniform circular thing, and I know the radius of my orbit, then I can actually find the magnitude of the acceleration necessary to sustain that orbit. And we can check that this is actually truly an acceleration just by checking units, right? So I'm going to use my brackets to denote units. So the units of A are equal to the units of V squared divided by the units of R. That's meters squared per second squared divided by meters, which gives me meters per second squared. So it is the units of acceleration. So this formula, in a lot of these circle problems, you are basically going to boil down to using this formula. So just this is a really useful one to keep track of. Okay. So that's the magnitude of my acceleration, but I haven't yet specified where exactly my acceleration is pointing. I've just said that, okay, this thing's moving in a circle, so its velocity is changing. It's changing in direction, not magnitude. But we don't actually know, what that acceleration points in, but we just know that it has a magnitude equal to this. So the question is now, what direction does A point in? Okay. So where does acceleration point in uniform? Okay. So I'm gonna try to draw my diagram one more time just so we can see what this looks like. Nice. Okay. So first I'll go ahead and draw R. So, okay, so my center of rotation is this. So you can think of this as like the center of the Earth or the sun or whatever your orbit problem is. This is what I'm orbiting around or what I'm rotating around. So I'm just going to draw my position vector at 4 different times. So let's draw one here, 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 and here. So imagine, I have some satellite that starts out here, it goes there, then there, then there, then there. So it's just 4 different points in the orbit. So these are all going to be okay. And we saw before that the velocity always pointed tangent. Yeah, so I'll just draw the first 2. Okay, so this is going to be a right angle. Okay, so the acceleration, so the velocity, if I draw a time series of what the velocity looks like over time, right? So at this first point here, the velocity just points up. At this later point here, we can see the velocity points to the left. And it turned out that if I were to draw these intermediate points like here, here, and here, I get something like so the velocity as a vector is twirling around as well. Likewise, if I draw the position over time at those same points, I'll see something like okay, so interestingly enough, the velocity, right, is sort of rotating one way and the position is rotating out of phase with it. And that's again because they're always at 90-degree angles to one another. Okay, so what's interesting about that is that the acceleration then is basically going to be what's causing this vector to twirl as it goes through this orbit. So it goes there and there and there, and then maybe there. So if I draw my acceleration on this diagram, it turns out that my acceleration always points this way. So it always points opposite the r vector. So I'm just going to draw that here. So if I draw that as a time series, then it looks like during uniform circular motion. So what does that mean? It means that my A points as negative r hat. Okay, so in other words, if my position vector is at any given time, if my position vector is pointing out here, my acceleration always points towards the center. And this captures this intuition that this velocity vector, right, which is changing over time, is always being sort of turned towards the center of rotation, right? So that velocity vector is constantly twirling around. Its length stays the same. It's just the direction it's pointing. And this acceleration vector is always sort of steering it towards the center of the circle. And so just like the velocity vector is a constant length vector that spins around, the position is a constant length vector that spins around. So is the acceleration. The acceleration is constant, it's always equal, or the acceleration magnitude is constant and equal to v squared over r. And it's also a vector that's just spinning around as the object orbits over time. So that means that I have an acceleration. And, whoa. I don't know if that's on a timer or something. Spooky. So this means that we have this condition that A, which is just the magnitude of A, is constant, and it's equal to 2 other constants, which is v squared over r, but A is not constant. Okay, so uniform circular motion, it's a little bit, kind of weird, but it has this nice property where all of our kinematic quantities we care about, right? Position, velocity, acceleration, all of them are constant magnitude, and they're all quite literally just spinning around. They're just spinning around out of phase with each other. And so you can imagine, it might be nice to try drawing in like intermediate cases here to see what they look like. Okay, so that's uniform circular motion. But the key thing to know is basically, we can basically write it as one expression, which is that the acceleration in uniform circular motion, sometimes you'll see this little c to emphasize circular motion, equals v squared, which is a constant, magnitude of velocity stays the same, r is a constant, and then I'm going to put negative r hat here. So I'll just simplify that and put negative v squared over r hat. So if you want to write uniform circular motion as a vector equation, you can just write that. And that captures the two things to know, which is that the magnitude stays the same, but the direction always points towards the center of your circle. Okay. So that's uniform circular motion, and you'll sometimes see this called, in some books, this is called the centripetal acceleration. And we won't talk about this today, but one clue here is that we know from Newton's laws that if you have an acceleration, you have a force. So this implies that the fact that I have acceleration means that I have a force acting on me, causing me to turn. And so you might think, oh, I'm just moving at a circle at a constant speed. Why would I have a force acting on me? But this means that in order to spin a vector around, even if its length stays the same, you have to have a net force, which is a little bit weird and gives rise to some of these weird problems. We'll talk about this more when we get to things like orbits and I think a couple of lectures. But this is just something to think about, which is that if you have a centripetal acceleration, there's a hint that there might be a force active in your system somewhere. Okay, but setting that aside, now that we've talked about this idea of having centripetal acceleration, so that's this acceleration that causes you to spin around over time, we're now in a position that we can talk a little bit more about what rotational motion really entails. And we saw a preview of this on Friday when we showed an example of finding angular rotation rate as a function of time. But we're going to get into this a little bit more granularly today because there's a very nice connection between rotational equations of motion and the kinematic equations that we saw the first week and a half of class. Okay, rotational motion. Okay, so if I have an object that's undergoing rotational motion, there we go. I'm going to just draw this on a nice coordinate system that hopefully will be a little bit, yeah, nice. Close. Okay. So I'm going to just draw x and y. You'll sometimes see a convention used where we define this position of the object orbiting as r. So again, this is just my vector that's always going to point towards my object. So here, if my object is there, it points there. But if my object were to orbit and end up there, it would point there. This is my current angle. And if I'm interested in going from A to B, I can define a quantity called the arc length, S. So I'm going to say S equals arc length, which is defined as the length that I traverse to go from A to B. So it's how much my straight line how much my curved motion traveled through space in units of meters. Okay, so the big thing to know about the arc length and everywhere it comes up is that the arc length obeys this property that if theta is my angle, then that is always equal to S over R, where S is the arc length and R is the radius. And in this case, it's a constant value because we're just using the norm of that expression. So that might seem like kind of a weird relationship, but just to see what we mean by this, why this might be the case. So here I'm defining theta as my angle of how far I've orbited after some amount of time. So one case would be the case where I go all the way around. So I do a full revolution. So that specific case would correspond to going 2 pi. So in that case, the question might be, how far was my arc length at that time? And I actually can solve that analytically, right? Because I know that the circumference of a circle is just equal to 2 pi r. And then I divide by r, and I just get 2 pi. So 2 pi equals 2 pi. So it looks like my equation holds, at least for the case of going all the way around. So this is nice because this is just this is sort of a general version of that, which is I can always find my angle in terms of my arc length divided by radius. Conversely, if I'm just given r, I can find, or if I'm just given r and theta, I can find s. So I can basically use this equation to go between arc length, radius, and how far I've gone along my circle. And this can come in handy sometimes. And I'm using this convention, by the way, that because I said 2 pi here, that means that I need my angle to be in radians for this formula to work. So I'm going to put a note on that. And the reason for that is because radians are really defined such that going all the way around a circle is 2 pi radians. And I need that in order for my 2 pi r formula to be correct. Okay. So if we want to think about this in terms of, so this equation as I've written it here is purely in terms of non-vectors, right? It's the magnitude of the arc length, the magnitude of the radius, the magnitude of the angle. But it turns out that we can think of theta s as vectors. And this is going to be purely a convention. So this isn't something that I think is super intuitive, but this is useful for keeping track of your vectors on some of these rotation problems. So generally speaking, if I have a coordinate system, so I'm going to try to draw this really nicely. So let's call that x, y, z. And these are my unit vectors. There's y hat, there's z hat, there's x hat. And this is my coordinate system. So these are all little right angles to each other in the plane of the page. If I have my rotational motion happening in the XY direction, so I'm trying to draw, I'm basically taking my diagram and trying to draw it flattened down there. If I want to think about theta as a direction, then I usually will use the convention that theta hat points up along the center of rotation. So theta hat points out along the center of rotation. Likewise, if I want to think about S, so if I draw my little radius vector, so there's R, I usually think about S as tracking the direction that the velocity would be in. So I'm going to just change colors to make this easier to see. I guess I used red here. So S is going to point that way. It's going to point tangent to my radius vector in the same direction that my velocity points during circular motion. So then S hat, which is just the unit vector, so that just tells me direction. This should point along the orbit tangent, and remember this tangent in the sense of that it touches the circle at one place, tangent to the circle. Okay, and you can combine all of these relationships into a single formula, which says that S, the full vector, is equal to theta written as a vector cross r written as a vector, where r is, again, probably the most intuitive of these quantities, right? That's just the position in the circular motion. Theta is this vector we've defined to point along your trajectory. So at every point, wherever I go in a straight line, tangent to the circle defines the direction of S, and then theta points out of the page. And so if I were to take this diagram and flip it so that now it looks like this, so more like my other diagrams, if this is my R, I always, by convention, say that theta points out of the page or up around the center of rotation. And so I can use the right-hand rule to find that theta cross R is equal to S hat. Okay, so this is just defining a coordinate system that matches what we use for the uniform circular motion, but we're going to use this S equals theta cross R to bookkeep which direction things point. Yeah, what's up?
If you were to give like a real life example, just like really just give us a distinct difference between rotational and uniform, what would you say?
So I think that the rotational motion is so uniform circular motion is rotational motion. We're just defining the coordinate systems again. So this same coordinate system you could use to describe uniform circular motion. Yeah. Okay, so the reason that we want to define this so explicitly is because if S is the let me get my colors right. Arc length, R is the position, theta is angle as a vector, where that vector just points out along your rotation axis. Then from that, we can define the angular velocity, which we saw briefly in the record spinning example or the propeller spinning example on Friday, where the angular velocity omega, the vector, is defined as the derivative with respect to time of theta, the vector, which is equal to d little theta dt in the theta hat direction. So what does that mean? It means that angular velocity points along rotation axis. So if I draw my little spinning record example, so I don't know, this is my spinning record, it's spinning that way or something. So if it's spinning, the angular velocity vector points up, but that doesn't mean that the motion itself is pointing up. That just means that we're bookkeeping the center of rotation. So angular velocity always tells you what axis you're rotating around, and it also tells you how fast you're rotating around. So that's how fast I rotate, and that's in radians per second. Although you can convert that to rotations per minute or something if you so choose, plus my rotation axis. Okay, so just like all vectors, you have a magnitude, how quickly I'm rotating, and then you have a direction, which is just the axis of how you're rotating, and that's all that omega tells you. So this formula comes in pretty handy, especially in a lot of these sort of weirder rotation problems that come up. Okay, so now that we've defined all these quantities, and we'll use these more granularly, but I just want to list these out to sort of emphasize this connection, right? So I've just defined, the equivalent of an angular velocity. We saw velocity previously. We defined here an acceleration, and we saw acceleration previously. It turns out there's a bunch of analogies you can make between rotational motion and translational motion. So I'm going to start by listing out these connections just so we can see them. And then in the next 2 classes or so, we're actually going to use these for a bunch of different problems. Okay, so I'm just going to draw 2 columns. So we'll say translation, rotation. Okay, so in translational motion, the first equation we talked about was the case of constant velocity. So these are all these problems that said, you're speeding down the highway at 60 miles per hour at a constant speed or something. So for that, we had this nice formula that x of t, so where I end up, is just equal to where I start out, x naught, plus my constant average velocity times time. And this is again assuming that that's just a constant, so velocity isn't changing. So we have an equivalent thing for rotation, which is that if I have constant angular velocity, then we have this formula that theta, so my angle as a function of time, is equal to my theta naught or my theta initial plus omega t. So again, there's this nice similarity there where it's how much the angle is changing, not my position, but it's basically the same equation with just different terms in it. Because that's the case of constant velocity. But most of the kinematics problems that we saw that were, a bit harder were the cases where we have non-constant velocity because we have acceleration. So for the case of non-constant velocity, but constant acceleration, this is where we started to use some of our projectile equations, right? So in this case, we had the formula for velocity as a function of time, which was equal to the velocity you start out at plus acceleration times time. And then we also had this other expression that gave you displacement as a function of time was equal to your initial displacement plus your initial velocity times time plus 1/2 a t squared, assuming that acceleration is constant. So these were our two projectile equations that we used before. So we can do the exact same thing here where we have non-constant angular velocity. And in this case, we have this equation that omega of t equals omega naught plus the angular acceleration alpha times the time. So again, this formula is very similar to that formula. It's just using the angular velocity and the angular acceleration instead of normal velocity acceleration. And then likewise, we have an almost identical formula for the angle, which is a kind of equivalent to position as a function of time. And that's equal to the initial angular position plus the initial angular speed or angular velocity plus 1/2 alpha t squared. So these are very, very similar. And in fact, if you wanted to, you could even derive analogous quantities for all of the other kinematics equations. So one that we sometimes see is this v of t squared equals v naught squared plus 2a x of t minus x naught. And if you wanted to, you could derive an equivalent expression for this. And I'll let you go ahead and do that substitution, but you just are going to replace, wow, okay. You're just going to replace these with angles and vice versa. And so basically every one of your kinematic formulas you can use for angular motion, you just want to substitute displacements, you convert to angles, velocities, angular velocities, accelerations, angular accelerations. So it's just a one-to-one comparison. All right, cool. Thank you.